Hi everyone and welcome back to this year's edition of KVIT Conference. We started the morning by discussing AI and what's going to happen in the future with some experts, and I hope you had a chance to calm down, have some coffee and clear your mind, because now we're delving even deeper into the AI question of what is possible and what we think is going to happen in the future. And with me I have one of the foremost experts on this subject. Fredrik Heintz is a professor here at Linköping University, but he's also renowned all over the world for his expertise on these questions. And we're incredibly happy to invite him here with us today. Fredrik, welcome.
Thank you very much.
Take it away.
Thank you very much. So it's a great pleasure to be here and to actually be in a live studio for once, and not sitting in my bedroom as usual. As was introduced, my name is Fredrik Heintz, and I'm a AI researcher here at Linköping University, where I've been doing AI research for more than 20 years. So we've been working a lot with autonomous vehicles, especially unmanned aircraft systems, where we had fully autonomous unmanned aircraft systems, in our case helicopters, more than 15 years ago. So today I lead a research group studying different types of technical aspects of AI, but I'm also very much involved in policy questions around AI. For example, I've been a member of the European Commission high-level expert group on AI. I'm also the president of the Swedish AI Society, and I'm doing research projects together with researchers from many different fields, including Stefan Larsson in Lund about the kind of legal and consumer aspects of AI. Also here at the university with Björn Una Linner about the geopolitical aspects of AI and so on. So what I wanted to do here today is to kind of give somewhat of an introduction to what is AI and tell a little bit about what I see as where are we going. Why are we here at all? Well, I think it's because you have seen applications such as self-driving cars or computers that beat the best humans in games like Go, chess, poker, Jeopardy, Dota, StarCraft, and so on and so forth. And just wait a few weeks or a few months and the computer will have beaten us in yet another game. The last one was some Chinese game that I never heard of that apparently the computers are beating the humans again in. And of course robots that looks a little bit scary and might take over the world. I would not be particularly worried about that, at least not yet, because the battery time for these robots are in the order of minutes. So if they want to take over the world, they either have to be really fast or have really long cables. So I'm not particularly worried about that at the moment. And of course I should say that behind all of these really impressive applications are this concept of artificial intelligence, AI. And as a first order approximate definition, I would say that AI kind of is where you want to get the computer to do things which currently only people can do. So we really want to push the frontiers of what the computer can do. I will talk more about definitions later. A second image that I'm using often is this one, and this is KG, 19 years old, after he lost against Google DeepMind's AlphaGo about 3.5 years, I think it is now. And he looks a little bit sad. And in an interview after the contest, he said that he felt that he would never have a chance against the computer because the computer was playing like a god. And of course, this is a very interesting statement from many different perspectives. But for me, I mean, he's 19 years old. He should still have quite a potential to develop and become even better. But he felt that he would not have a chance. Actually, this has actually led to consequences. So last year, Lee Sedol, one of these other famous Go players that AlphaGo has beaten, actually decided to quit. He felt that even though he could become the best human Go player in the world, he would still not be the best player, so therefore there was no point in continuing. But actually, this is not the main point I want to make with this example, but rather I want to make the case that how should we as humans interpret what the computer is doing, whether what the computer is doing is good or bad. Because in the games, there were several times when the expert commentator was saying things like, haha, the computer made a mistake. A human would never play like that. And of course, you understand that the computer won. That's not the key part. The key part is how should we determine whether what the computer was doing was good or bad. In this particular case, it was obviously the case that this was a good move. The computer won, but the humans still interpreted this as a at least potentially bad move. And why is that? Well, it's because we don't compare to what's necessarily like objectively good or bad. We're comparing to the way that we do things. So if the computer is doing things in a different way than we do it, then we get suspicious and question what the computer is doing. And I think this is a really interesting question because it's not only detecting whether the computer is doing something good or bad, but also on what basis. Assume that you are, say, a doctor and you have a recommendation system which gives you a recommendation. And then on what ground would you challenge this definition? Or sorry, not this definition, but this recommendation. And I think that's a really interesting question because in a sense, a computer probably will be able to make recommendations on a much larger data set, much larger amount of information that we can do. But still, I believe we still have an advantage, but it's not obvious how to deal with this. And the second observation is, of course, that the computer obviously were able to come up with new and creative ways of playing the game. It was not just copying the way that people were playing it, but actually coming up with new ways of playing the game. So I would argue that the computer is also creative. The second example here.
Hi, Sofia.
If you could turn off the sound on the video, I would appreciate it. So this is an example of a humanoid robot. It's called Sofia. Again, I think this video is like 4 years old, almost at least. And the purpose here is to show that it's possible to build robots that look very much like people. Of course, doing artificial skin or kind of building human-like robots, that we have been able to do for a long time. What is new and what is kind of the difference here is to make the movements around the mouth, the nose, and the eyes sufficiently close to the way we move in order to make it believable and to not end up in this what's called the uncanny valley where it's extremely uncomfortable to watch. And why is this important? Well, because we use our face to communicate, non-verbal communication. Especially we use expressions to express what people interpret as emotions. So what you can see here is the kind of emotional capacity or register of this robot. So again, what's interesting here is this, what can be done? And this is a clear example that it's possible today to build a robot, and it's actually been possible for a few years, to build robots which can behave in a way that if we as humans would interpret it as if it had feelings. So I would argue that you could build a robot that, for example, if it were to walk around, now this particular robot is only a torso, so it doesn't have any legs, but assuming that it had legs and it was walking around, bumping into a table, for example, saying, ouch, and then making a face like one of the faces the robot made in the video. And it would make perfect sense to us to interpret it as this robot were hurting itself. Or if you're asking it a question, and the robot does not understand the question, it's making one of these, I don't understand the question faces, and makes, like a noise like that. Again, it would be meaningful communication for us. So I would argue that it's possible to build robots that can express things that we interpret as feelings. Of course, this does not say that they have feelings, because we don't know what feelings really are, or maybe there's, I don't know at least. And as far as I know, there's no test to determine that if you satisfy these criteria, then you have feelings. And I would argue the same thing, it goes for consciousness, that you probably can build a robot that behaves in a way as if it had a conscious. But of course, it does not say anything about it actually having a consciousness, because that's a completely different question. One interesting comment there is that if you look historically, over time, we are attributing feelings to more and more types of animals and creatures and so on. That from the start, we thought it was only humans. Then we have been gradually expanding this to more and more categories. So who knows what happens in the future? But I would say that it is possible to build robots that express things that we can interpret as feelings. My third and last example in this particular case is the following. So this looks like faces of humans, just like you and I. But what's interesting here is that this is faces of people that do not exist. And it actually even comes from the URL thispersondoesnotexist.com, and you can go to this page and you get a face of a person that does not exist. You can do reload and you get a second face of a person that does not exist. So why is this interesting? Well, first of all, it really blurs the line between what's true and what's fake. So today it's possible to generate text, sound, images, videos that are more or less indistinguishable from something that you will record in real life. And this, of course, puts a lot of challenges when it comes to detecting or to determining what you see, whether it's true or false. And actually, I would also argue that it kind of blurs the lines between what does it mean to be true and what does it mean to be fake. Because, of course, photoshopping images is something that we do regularly. I mean, I would expect in most magazines and so on, most photos are photoshopped. So when do an image stop being true? How far from some reality and so on can it come before it becomes fake? So I think this is a very interesting challenge, but it also can be used for positive things. For example, there are a lot of cases where we have sensitive information, for example, regarding individuals' privacy, that we don't want or we're not allowed to share potentially sensitive information. For example, it might be a medical journal or medical history of people, and that this could be very valuable to researchers to develop new drugs or to improve healthcare in general. But due to privacy reasons, we don't want or we are not allowed to use this information. And then the idea is that we can generate synthetic patients, just like we're generating synthetic images of people. We can generate synthetic patients with the same kind of, that they are similar enough to real people, so that we can actually use this in, for example, medical research. And I think this is a very interesting avenue and a positive use. A second use that I've seen very recently was when journalists were interviewing a person, and the identity of this person could not be revealed. And of course, normally you would either blur the face or put them in behind a curtain or something. But in this case, they used these kind of deep fakes to generate a fake face and kind of fake voice and so on for this person. So they could interview it as if it was a real person, but without actually revealing the real identity of this person. And actually, I think this is a general thing regarding many of these technologies, is that they're both very useful and good applications or usages of these techniques, but they can also be used, for example, to fool people. I mean, to trick you into giving away money to someone that you think is your relative, but actually turns out to be just a fake voice or even fake images that you could talk to. So that, I think, is a very interesting aspect here. And so, with these examples, I now want to talk a little bit about what is artificial intelligence. So there are many different ways of defining AI, and actually some people claim that there are probably as many, if not more, definitions of AI than there are AI researchers. And since I actually think that there is it's interesting they cover different aspects. I therefore have included 3 different definitions here. So the first one is from John McCarthy, who is one of the founders of the field, which is usually attributed to the Dartmouth Summer Conference in 1956 that he organized together with a few other people. And he defined artificial intelligence as the science and the engineering of making intelligent machines, especially intelligent computer programs. And to me, this kind of summarizes the kind of key part. We really want to build intelligent machines. The main criticism against this definition is that there is no universally accepted definition of what intelligence is. I was looking into this and I found a survey, I think it was from 2007, and then they had identified 71 different definitions of intelligence. So just like there are many definitions of artificial intelligence, there are also many definitions of intelligence. But we can take one concrete example, assuming that we have one of these non-verbal IQ tests, basically finding patterns like there are different types of symbols in different configurations, and then you're supposed to predict what is the next combination of symbols or dots or something like that. I mean, this is something that computers are extremely good at. So if you determine intelligence by that kind of test, a computer will probably get a full maximum score on that. On the other hand, as far as I know, there is no robot that can tie a pair of shoes. So that is something that is much harder. So the second definition is from the European Union. And they defined AI as referring to systems that display intelligent behavior by analyzing their environment and taking actions with some degree of autonomy to achieve specific goals. And to me, this highlights the way that these systems normally work. First of all, they're designed by humans to achieve some specific goal given to the system. Secondly, they work by collecting information from the environment, which can be digital or physical, and then analyzing this information in order to determine what should be done in order to achieve these specific goals. And then after making these decisions or analyzing this data, the next question becomes how to actually do something, to act. And here it's also about a degree or a spectrum of different types of autonomy, all from the kind of, some sense, lowest form of autonomy in the sense of decision support, where basically the computer just suggests something that the human then can decide to act on or not, all the way up to, say, for example, a self-driving car, which actually make autonomous decisions on its own, and everything in between. So I think this kind of covers that part. The third and final definition that I present here is from AAAI, which is the Association for the Advancement of AI, previously known as the American Association for AI. And they define it as the scientific understanding of the mechanisms underlying thought and intelligent behavior and their embodiment in machines. And to me, what's interesting here is that they're not only looking at intelligent behavior, which is basically what the system can do, from an external observer point of view. If it acts intelligently, let's assume it is intelligent. But they also look at internal processes, which I guess is very much relevant to this particular conference, because to me that's really on the cognitive science part, understanding the cognitive processes of how do we make decisions, how do we plan, how do we learn, how do we interact, and so on and so forth, and really understanding the underlying processes as well. So together, I think this covers many different important aspects of AI. Of course, there is a lot of discussion regarding whether there has to be one definition of AI. Personally, I don't see the real benefit in that, because to me, the really kind of major contribution of AI is really to explore this unknown, uncharted territory, which we don't really understand what it is. We know we want to go somewhere, but we cannot really express in detail exactly what we want. And as soon as we're able to formulate clearly defined scientific problems, we kind of spin off separate research areas, which is much more. And actually, I think that is probably what we should see here as well, that we kind of define for different purposes. We can provide specific definitions, but for this general area, I think it will be challenging. So what are then the major applications that we see today? I would say that the major applications, the areas where we've made the most progress the last 10 years, is really in what I would call perception. So understanding the world around us, especially when it comes to, for example, computer vision. So doing object recognition, doing semantic segmentation, and so on and so forth, to really kind of finding and trying to make structure out of these unstructured images. The second area is voice recognition. So it's basically the same as for images, but for sound and audio, trying to understand what we say. So of course, thanks to these improvements and breakthroughs, we now are able to talk to our devices, and usually the device is, as if not better, at least as good as we are in interpreting what we're actually saying. Which also leads to the third area, namely natural language processing. So this is, of course, an area which, I mean, all these areas have been studied throughout the history of AI already since the 50s. But again, where I think that we have seen major progress. And especially when it comes to, for example, this GPT-3 model that you might have heard that was released this summer, which is really impressive when it comes to generating new text. You basically ask it a question and it writes out a paragraph of answer based on what you said and based on what it has seen before. And this has, for example, been used by The Guardian to write a story in The Guardian. And I mean, I think these are all areas where I've seen impressive improvements. Of course, there are a lot of challenges, which I will come to later, but I think there is today, I mean, I think the difference today compared to, say, for 20 years ago is really that it's the kind of how hard it is to get these things to provide value to an organization or a company has reduced significantly. And today you can take more or less finished, almost finished solutions and apply them to your problem and get value out of it relatively straight away. But I wanted to get back to this question of, or to this example of computers playing games, particularly computers playing chess. And of course, this is an area where we as humans haven't had a chance against the computer for at least 20 some years, since Garry Kasparov lost against IBM Deep Blue in 1997. But what's interesting is, of course, that the quality of human chess playing is increasing. Actually, the interest for human chess playing is also increasing. And one of the absolutely best players in the world, Magnus Carlsen, he's one of the kind of hypotheses why he is so good is, well, he has been playing against the computers since he was a small child. So he is the human that is the best at playing like a computer, and therefore he's the best human chess player. But what my main point here is actually that if you combine humans and chess-playing computers, they're better than both the best humans and the best chess-playing computers. And actually, this was seen in a competition that was organized by Garry Kasparov himself in order to kind of see whether we could provide some added value there. And I really think what's important here is that it's not a question about either AI or humans, but rather it's how can we combine AI and humans together so that we can solve these challenging problems that we're facing much better than what we could do on our own. But what's important here is to realize that it's a different skill to play chess with a chess-playing computer compared to playing it on your own, which means that you need to train, or you need to learn how to do this. And you also probably will need to change the way you organize your work in order to leverage these tools. And the example I've often used here is a study that was done in Swedish schools about introducing computers into the classroom. So basically, they tried to introduce computers into the classroom, and what they saw was that if you try to use the kind of previous, using the same pedagogical methods, your results were worse if you introduced computers compared to not introducing computers. However, for those teachers that actually adapted their pedagogy and adapted the way that they were teaching to take advantage of these tools, they got much better results. So what this means is that it's not just about introducing technology, but it's about changing the way we work and learn to collaborate and solve problems with computers. And that's also why I've been very much active in the kind of digitalization of school, especially when introducing this concept of computational thinking, which to me really encapsulates these skills and attitudes, which allows you to effectively collaborate and solve problems together with computers. And we can see the same results if we do, for example, medical analysis, that humans and diagnostic systems, automated diagnostic systems, make different mistakes. So if we combine this, we get a better result than we would with either or. So it's really about humans and AI. So that was the. Now let's talk a little bit about the challenges and how to deal with that. So I mean, one challenge is of course that these systems are still very brittle, which means that a small change in the input can get a large change in the output. So, for example, this is a famous example from Google, where they took their well-trained classifier, and that was correctly classifying this image of a panda. They added something which looks like noise, but actually isn't noise, and they got a new picture, which to us humans looks exactly the same as before, but to the computer looks completely different. And of course, the reason why it looks completely different is because the computer will not see kind of an image as we do, but rather it will see, I don't know, 1 million dots or 1 million triplets of integers, where each triplet is how much red, green, and blue there is in that particular dot. And then you get, if there are 1 million pixels, you get 3 million integers. And from that sequence of 3 million integers, it's supposed to tell you what's in the image. So actually, from the computer's point of view, the middle image is much more closer to what it sees. But the point here was basically that you can easily fool these systems. But of course, the purpose of this was to improve, because we could use this in a systematic manner to improve the way these systems learn. So this was the idea behind this generative adversarial networks, which today is kind of one of the main techniques and really fascinating technique that, for example, we use to generate this generated fake faces. So basically, the way it works is that you can see it as you have the police and you have the counterfeiters who try to make fake monies. When the bad guys are getting better at making fake money, the police need to improve their methods of detecting whether a particular bill is fake or not. And then basically get this adversarial learning that when one is getting better, it forces the other to get better. So basically what you do here is that you try to learn both a classifier to determine whether a particular example that you see, whether it is real or fake, and real here means coming from the original data set, or if it's being generated by the generator. And of course, the generator is also trained in order to generate more and more believable samples. And basically, the system converges if the discriminator is not able to determine that it's equally likely that this is a fake and this is a real data point. And this is then a technique which have been very much used the last 5 years. Another issue is bias. Of course, due to the fact that these systems are to a very large degree data-driven, it means that the kind of input data determines to a large extent how good the final result can be. And here we see a number of different types of biases. In some sense, the most common type of bias, in some sense, the easiest type of bias to deal with, what we can call like representational bias. It's called here dataset bias. Basically, where the dataset that you have used to train your system is not representative of reality. And here we have, for example, seen examples of facial recognition system which worked relatively well on white males, people like myself, but did not work well with colored women. And when they studied how can this be the case, they found out that developers who were mainly white males, of course, or not of course, but yeah, they were mainly white males, have mainly been testing the system on themselves. And of course, this is not a very good strategy, but it also is a relatively simple thing to deal with, because it's more about collecting more data and making sure that the data that you collect is actually representative of reality. What is much, much harder are those cases where reality is not the way we want it to be. For example, there have been a lot of cases, for example, with showing ads for jobs, and then it turned out that women were more likely to get an ad for a lower paying job, and a man was more likely to get an ad for a higher paying job. And again, when they looked into how was this system built and looked at the data that was used to train, it was basically using statistics from the actual labor market. And it was basically saying, well, men are more likely to have these kind of jobs, so therefore we suggest more of the same type of jobs to them. And due to the kind of salary discrimination that exists, they kind of got the higher paying jobs, or they were getting ads for them. And now the question becomes, how do you do something about this? Because it's not about collecting more data, because the problem is that the kind of what you're comparing to and what you're trying to live up to is not the way you want it. So someone needs to say, no, this is not the world we want. This is not the reality we want to see. We want a different reality. And then you basically need to generate data or manipulate data in order to get what you really want. And of course, this means that someone needs to make a normative statement and then also take the consequences for this. And I think this is where it makes it so difficult. I mean, in some cases, it's probably less controversial. But for example, take this discussion of filtering out hate speech on social media platforms. Who should define what hate speech is? And where do you draw the boundary? I mean, especially, for example, you have satire or you're just making a joke and so on. How do you make the difference between these? And actually, this turns out to be a really challenging problem. The second issue is, of course, how do we So, I mean, from my point of view, I think a large degree of the bias that we see in our systems today are mainly due to the fact that we as humans are very biased and our society is very biased in many different ways. And in some sense, I think this is a step forward because it's actually making this bias explicit. Now we actually see from an external point of view what we probably do every day anyway. And it actually gives us an opportunity to improve our human decision-making by analyzing our human decision-making in the same way as we analyze these computer decision-making systems. However, that actually puts a lot of demand on how we react to this. So there was this case in France where the French judicial system were basically making all the judgments available. And then some scientists came along and said, this is interesting. Let's analyze this data, and basically came to the conclusion that they were looking, I think it was some asylum decisions, and basically came to the conclusion that the judges are extremely biased, and that it did not matter that much about your actual case. It mattered much more which judge you actually got. And I mean, to me, this is not particularly surprising, but what's interesting was the reaction. So what happened? Well, first of all, the scientists tried to kind of get the response from the lawyers or the judges on the report. They didn't respond. And then they published the report. And then, of course, all hell broke loose. And in the end, it was actually made illegal to do research on how judges make decisions. So now there is a law in France that says it's illegal to do research on how individual judges make their decisions. So instead of actually fixing the problem, they made it illegal to study the problem. And to me, this kind of captured probably the challenges with us humans dealing with these issues. Another problem that has been discovered, so this was a paper from ACL, the Computer Linguistics Conference last summer, summer 2019. And basically, they were studying this state-of-the-art question answering system. They were asking a question, and then they were just changing a small part of this question, usually by negating the question or adding or removing a few words. And then they could discover that, these small changes made the system answer the question in the wrong way. And basically, what they analyzed or what they claimed is that basically these systems are learning simple heuristic rules. That, for example, if you use the same words, then it's probably a positive answer, and something like that. Or if you extend a question with some words, then it's probably a positive answer. So they were, again, very easy to make mistakes. And then what I think is more interesting is that they looked at the actual training the evaluation. So how were these systems evaluated? Because, I mean, these were systems that were getting like 95 plus accuracy. and still they were not able to answer these questions. So, and then they looked at the training data, or the validation data, and they found that most of the validation data were positive examples. There were actually very few negative examples, which means that if you asked the question whether the answer was negative, they were much less likely to make the right answer. So therefore, as soon as someone claims, oh, my system, it can do 99% correct, my expectation is always that, yeah, your validation data probably not covering the real problem. Show it when you actually get the same result on the kind of data that you do not control, but actually was kind of collected in a while. So that's something to do as well. And the kind of last example of challenges that I have here is the following. So the point here is that if you want to build these large-scale machine learning systems, the actual core machine learning part is usually small. And actually getting that competence, I do think, we have WASP and other initiatives really kind of pushing the scientific frontiers and making sure that we have highly skilled people on these kind of core machine learning and technical parts. But actually to get a real system to work in a real production setting or in a real service, you need much more, because you need to be able to do this kind of large-scale data collection. You need to do large-scale computations. You need to do large-scale monitoring of these systems after they are in production, and so on. So you really need this kind of large-scale data processing infrastructure. So to me, there is it's no surprise that the companies that are really pushing the boundaries for machine learning today in the real world, there are companies like Amazon and Google and Facebook and so on, because they have the compute infrastructure. So they have the infrastructure, and then adding AI or machine learning to that is a much simpler task than going the other way around, that, oh, we are a great machine learning team here, now let's scale this up. That's a much harder problem. And I also think this is a major reason why Sweden and Europe are struggling in some respects in this area, because we don't have those companies with this large-scale digital infrastructure. So what is then Europe doing? Europe has taken a very clear stance that we want AI, but we don't want any AI, but we want AI that's what we call human-centered and trustworthy. So we really want to develop AI to help us as individuals, as citizens, and so on. And if we look at AI in Europe from a somewhat outside perspective, we can see that actually AI research in Europe has a very strong record, and actually Europe is publishing the most papers in AI still. But of course, the change rate is much worse. So of course, countries like China and the US are accelerating at a much faster pace than Europe, which means that if we want to continue to be ahead of the curve, we really need to invest, and we need to speed up, especially. When it comes to competence, this is a general problem, and Europe is actually a netto exporter of competence. So we have quite good universities and so on, but we have a problem of retaining the talent in Europe and to attract them back if they've been abroad or outside Europe, coming back. That is where our challenge is, because compensation and we're not providing enough interesting challenges for them and so on. And this is also related to the fact that European industry is relatively low on digitalization, which means it's harder, as I showed in the previous slide, that it's harder to kind of start using these types of techniques because they don't have the digital maturity. And there is also very low private investment in AI. I don't have it here. These figures I have here are a bit old, but there are newer figures from the AI Index report, basically showing that the private investments in the US, I think, was in the order of $30 billion. The private investment in China, I think, was around $20 billion. And then towards the end, the European countries are coming. So that is a major challenge. So therefore, the Commission has stated that they are working to increase the investment in AI. So the goal is by 2025 to have a yearly investment of 20 billion euros per year in AI, and the Commission see that they are probably going to provide about 3 billion of these, which means that companies and member states have to contribute the other 17 billions. And of course, that is where a lot of the activities in EU and Europe is going on today. How do we increase the investment in AI? And the foundation for this is, as I already mentioned, that we want AI, but we don't want any AI. But we want this AI that we can trust and that we as individuals feel comfortable using. So therefore, they created the Commission created this high-level expert group on AI, which I was a member of, and we then defined that trustworthy. In order to be trustworthy, an AI system has to satisfy the applicable laws and regulations. They have to satisfy 4 ethical principles. And what actually I think is the most important part is that good intentions is not enough. You also have to have a robust and safe implementation of your system. And then, of course, these things are easy to say. I mean, a lot of countries and organizations are saying them. What we did was actually take 2 steps further. So the first was that we took this principle and defined 7 requirements. And then we also, from these 7 requirements, made what we called an assessment list, which is basically a set of questions that you as an organization or company or similar can ask yourself in order to do a self-assessment whether you satisfy these requirements or not. And there we released an updated version of this assessment list this summer. So I recommend that you take a look at that. And the 4 principles that we stated were respect for human autonomy. So this is really about that we should not replace people, but rather we should augment, complement, and empower people. That's the point. Secondly, we should, of course, prevent harm, and that means both physical and mental harm, that these systems should be safe to use. The third is fairness. So, of course, we want equal and just distribution of both the benefits and costs. However, of course, this is one of these topics which is really challenging to define what fairness really means. And fourth, we have explicability. So this is really about this. We want to be able to understand what these systems are doing, why they're doing it, on whose behalf they are doing it, and so on and so forth. So it's about transparency and explainability and all these concepts. So actually, my intention was that I would talk a little bit about the research challenges related to this, but I see that my time is kind of running out here. So I will not cover it in that much detail as I expected. But when it comes to this respect for human autonomy, I think we have very interesting questions regarding, for example, to human-AI interaction. So, for example, today it is quite popular with these apps that are kind of trying to get you to eat more healthy or to exercise more and so on. So in some sense, what you're doing is that you're delegating your decision making to an application or an app in order to override your own decision making, because you realize that my own decision making is probably not going to make these choices, but still I wish I were making these choices. And they are probably perfectly okay if you as an individual user are making these decisions, because then it's you made this decision. But of course it becomes much more challenging if, for example, the government would say that now we want everyone to exercise 10 minutes every day. Or if your insurance company says that, oh well, if you install this app and you eat healthier, if you exercise more and so on, then you get a lower premium. Then it becomes much more questionable. So I think this is really interesting question regarding like nudging and interaction and so on. When we have this prevention of harm, I think this concept of AI safety, I mean, is really interesting. So in some sense, how do we make sure that these systems, which are basically designed to be able to make better decisions that we do, how do we make sure that they actually make decisions that are truly good for us and not only good for the some limited sense? And how do we verify and validate these kind of systems? So I actually have an industrial PhD students working on this particular topic. How do you verify that your system, which works perfectly fine in your kind of testing and evaluation situation, how do you make sure that it also will work in the real world? With all the kind of both known unknowns, the things that you can think about could go different, but also your unknown unknowns, the things that you're not even aware could happen, and so on. How do you deal with that? So that's a really interesting problem. Fairness, then of course we have all these issues of accountability, transparency, and explainability. So when it comes to fairness, I think, just the key question here, so do we want equal division of resources, or do we want equal outcomes? I think that's the first question you need to answer. Just answering that question is not particularly easy. We could just see in the papers today discussing this, how much money the schools should get for each pupil. And basically today's system is equal amount of money per pupil, but then of course in reality they have different challenges and they're kind of incurring different types of costs. So now there's a discussion, maybe we should change this. It should not be equal amount of money per student, but rather we want to get this kind of equity in the outcome instead. And then you can break this down in much more detail. I would just skip explainability, privacy preserving synthetic data generation. And rather spend the last few minutes talking about how do we move forward. And moving forward, I think what's interesting is to take this example of Daniel Kahneman and what he wrote in his book, Thinking Fast and Slow, about this System 1 and System 2, where System 2 is this slow, deliberate, explicit, often logical reasoning. So in some sense, it kind of encapsulates this ideal analytical way of reasoning, which I would argue is also the kind of ideal that what many people today call like kind of traditional AI, the kind of reasoning-based AI, is really focusing on understanding and mechanizing this type of reasoning. But on the other hand, we have these other types of reasoning in the System 1, which is then the fast, automatic, but often opaque. So we have no introspection into this. So for example, the best example is probably intuition. So often in many cases, we might intuitively feel what the right answer is. But then after further thinking or contemplating, we might, maybe it wasn't right. But of course, in most cases, it is right. Or take our perception system as an example, that we can often identify a person which is just a small dot on the horizon. And we say, that's my friend. And how can you do that from a few pixels? And still you're often correct. So this is an example of this System 1. And I would say that this is the type of systems that you can build with this kind of data-driven machine learning-based approaches, which means that they work pretty well most of the time, but sometimes they fail kind of spectacularly. So of course, the major challenge here is how do we combine this? How do we take the advantages of both these systems and move forward based on that? So from my perspective and what I'm working on is really that I think we need to build causal models. We need to go from correlation to causality. It's not just about finding these correlations. Then in some sense, if you stop selling ice cream, then you will not get as many people that drown in the summer because there is a correlation between those two, but of course there's no causality. And we want to build these causal models both based on data, but also on knowledge, because we have spent centuries doing scientific progress. Why shouldn't we leverage all that we have learned in those times? And then we want to use these causal models both to explain the past, explain what has happened, explaining this data relative to these models, but also to do predictions about what is likely to happen based on these models. And why is this then important? Well, to me, the most important part is that if we want to make the best possible decisions, considering that amount of information that we have available to us to make decisions are growing exponentially, we basically have no choice. So if we basically have two choices. The choice is either between making worse and worse decisions based on the available amount of information, or learn to kind of leverage these tools. And actually, I think this graph here is also very interesting from an educational point of view. Because basically, if we assume that the amount of knowledge in the world doubles, say, every 2 years, which from what I understand is actually a conservative estimate, it means that if you finish your education, say you're a doctor, a medical doctor, you finish your degree and you know everything when you finish your degree, and then you wait 2 years, now you only know half. After 4 years, you know a quarter. After 6 years, you know an eighth, so a little bit more than 10% after 6 years. And then, of course, it just gets worse. And actually, as far as I know, there's been studies on general practitioners in the US. And basically, your chance of surviving is negatively correlated with the time since they took their GP. So basically, the longer that basically the doctors are making decisions on what they learned at university more than what they learned while working. And this does not apply to specialists, but this applies to general practitioners. So this means that we will need to learn much, much more after we finish our education than what we do during. So actually our education, that we do, it's just a small part of what we need to learn in order to really leverage all the information that exists. So I think that that's an interesting challenge for our educational system that I'm happy to work with on. I will skip a bunch of things. If you want to learn more, we have this Elements of AI course. And of course, since I think that education is one key part, I think this is really important. I also want to say that I think Sweden is starting to get a very nice and coherent innovation, competence and research ecosystem with the universities, this large WASP initiative, which is a private initiative of about 5.5 billion Swedish kroners, where most of it comes from Knut and Alice Wallenberg Foundation, and it's now been extended to 15-year-long project until 2030, with a goal of educating at least 600 PhDs in this area and recruiting an order of 60 research groups coming to Sweden to do research in AI autonomous system software. Then we have this AI Competence of Sweden working with professional education. We have what was previously known as AI Innovation, which is now known as AI Sweden, which is really accelerating the use of AI in companies and organizations. And I'm also involved in the AI Sustainability Center. So, there are a lot of things happening. Likewise, on the European level, there's just been started 4 networks of research excellence centers on different topics in AI. And I'm leading one of them, the one that's called Taylor, on the foundations for trustworthy AI. And of course, we truly believe that in order to achieve this, we need to integrate learning, optimization, and reasoning. So I'm spending some time on coordinating that. And so to conclude, actually, in some sense, sometimes I get a bit worried that Swedish companies and people in Sweden are doing too well, because it's when you are at your height, your peak, that is when you have the chance to change, because that is when you have the resources to change. So actually, Patrik Ekemo from DIG, the Swedish Digitalization Authority, says that it's now that Sweden needs to change, because we will never have as much money as we have today in the public system. And if we don't spend it now, we will just get less and less money to invest, and basically we will not be able to sustain the welfare system that we have today. And I think that the lesson here is from Kodak. Of course, I could have used Facit with a local example, but that's too depressing, so I didn't. But basically, that Kodak had all the patents for digital photography. But then they looked in them, how are we making money? We are making money on paper and chemicals. Do you need paper and chemicals for digital photography? No. Well, let's sell those patents. And then, of course, digital photography and iPhone and so on came, and then Kodak went bankrupt. And I think what's really challenging here is that they were fully aware of it. But the problem is, who are sitting in the boardroom? Well, the people in the boardroom are those that made their career on paper and chemicals. And of course, they will make decisions based on their experience, because that worked very well in the past. But now you have a different situation. Then you need to make different decisions. And that, I think, is really challenging. So to conclude, I will not go through this, but what I really think is important here is that AI is here, and it will influence basically all parts of society. And we really need to make sure that this AI is developed in a way that can be trusted. And also, what I also think is important is that it comes everyone to benefit. So we really need, what I usually say is AI for good, and we need AI for all. Because in the end, it's not about AI or humans, but rather AI and humans together. Thank you very much.
Thank you very much, Fredrik. As always, it's so inspiring to hear you talk about these things. And I have a million questions, but I'm going to try to kind of get a few of them down, because hearing you finish off with a call to action, that's always a good thing. But if I'm sitting there now in front of my screen thinking, what can I do? I'm not a PhD. I'm not involved in this. Is there something I can do?
Of course, there are a lot of things you can do. I mean, in some sense, I think what's important here is to learn more. I mean, you can, of course, take this course, Elements of AI. We are now working on continuation courses as well. But what I also think is really important is that we need people with the kind of dual competences. So, for example, we need medical doctors that also know about AI. We need HR people that know about AI. We need lawyers and so on. So yeah, I really think it's important that we still have this kind of different specializations, but we need to combine that with this extra competence, and that you can see this combination. That is when you see the real difference. And that, I think, is something we can all
do. You need historians and behavioral scientists
of
as
course.
well?
Yeah, I mean,
so
we have all this.
That's a future career for me as well.
BUSP HS program, which is really about studying the kind of consequences and impacts of AI and autonomous systems. And there, that is a research program geared towards humanities and society, also social sciences and so on. So, as I said, I'm collaborating with Stefan Larsson in Lund, who's a social scientist. I'm working together with people at educational sciences, and we have other people here at Linköping University working on this kind of intersection of different topics.
Exactly, because that's the point we're trying to make, right? You can't squish this away in the corner for the computer scientists anymore. We're way past that, and it's actually a society question now.
Yes.
One of the things I was wondering, because you've been talking about this for quite a while, I think we met the first time at some Game Award thing years ago. Do you feel like the knowledge in society has grown about AI? Is it more of a common knowledge, or do you still face a lot of misconceptions about AI and what is possible and what the future might hold?
So I do think there is a challenge in people have a tendency, and I mean, I'd probably say that researchers are probably the worst, almost the worst there, and that's about overstating the consequences. I mean, in some sense, what you can do. And I mean, it's just to read the press releases of the major companies doing nice things, but then they say, oh, this will solve everything. And of course, that's very unlikely to be true. So I think there is a challenge of kind of expecting too much. But if we see, I mean, I think we have gone from being uncertain about what it is to at least go to the next step, namely, okay, we realize we need to do something, but what do we need to do? So I think there is a big change there in going from what it is to actually what should I do.
And you're starting to kind of tie it together with different fields and things, so it's easier to understand how will this impact me as an individual in the future? Where might I actually meet this? Because a lot of it, like you said, a lot of examples were sort of hidden within systems that we use. But
I would say that, I mean, today more or less everyone is using this. I mean, probably in your smartphone, there are probably 50 or hundreds of different kind of learning processes or things. I mean, there's so much going on behind the surface. And I mean, and most of it is not the type that you read about in the papers because it's just dull engineering work. And that's also kind of a worry about this kind of definition. So, I mean, this kind of expectation that the EU will put regulatory constraints on AI could also kind of have a lot of unintended consequences for these other types of applications that we don't really care that much about. But what we care about is usually the ones that we interact with on a personal level. And I mean, I would say that if you have, these search engines, I mean, that's a really amazing kind of AI application, or using different types of image recognition system, people taking pictures, and then you get to know what's in the picture, or as I said, using this voice recognition, you're talking to your phone or your computer. And I mean, all of these are powered by AI technology.
It's incredible how much is already infiltrated, and at the same time we have this misconception of what it can actually do. And I guess within the next couple of years we will see where it actually ends up. And this is one of the questions, like experts sort of debate this. General AI, yes or no? What do you think?
So I mean, from my point of view, I think in principle it should be doable. I mean, if we believe that intelligence is computation, then of course a computer can do it. So I think in some sense the question is intelligence computational or not? And I would argue that probably what we mean in some kind of idealized version of the term, yes, I do think it is. But I do think there are other aspects, namely this, that what you want to optimize for. And I mean, I don't think we are optimal, or we don't find a guaranteed best solution and things like that we often aim for in computer science, but rather, well, it's good enough. And then, of course, that's different. I mean, because then it's a question of what is good enough, and how do you kind of set these thresholds, and how do you determine what to optimize for, and these things. So this kind of meta reasoning parts, I think, is much more challenging, and I think that is probably looking forward for, I mean, the kind of interaction between humans and these systems. I think for us, it's really about what do we want the systems to do. I mean, in some sense, see it as this kind of oracle. I mean, I want something. Now, can you explain what you want in detail enough so that the computer can do it? Then, well, sooner or later, probably will be able to do it. But we need to be able to describe this and to kind of, push it in the right direction.
Exactly. It's great because a lot of the people who are watching here today are studying this, and this is exactly what they want to do. Well, last question. Are you optimistic or scared or both? The future for AI?
I mean, I said I'm mostly optimistic. So in some sense, the risk I see is that we actually, in some sense, become too afraid, or we're not able to leverage this technology. So in some sense, if I'm afraid of something, it's more this that, oh no, we need to wait and see. We need to have everything proven and fixed, and then we can do it. And I do see some tendencies of that, especially in Sweden, and especially when it comes to the kind of public sector, that no one wants to be first. As soon as someone shows, oh yes, this will work, then everyone kind of jumps the train, but no one wants to be first.
So we need to be bold.
Yes, we need. I mean, and we really need leadership. So I mean, I don't see this as mainly a technical challenge, but more an organizational and leadership challenge. How do we get the leaders who dare to move ahead? And yes, they will take some risks, but and they will fail. Some of them will fail, but it's only through this failure that we will learn and really be able to understand how we should take the best advantage of this technology.
Wow, we have a really exciting future ahead of us. And I hope we meet here again and talk about this in a couple of years and see what's happened. We're going to move on to a break. It's time for lunch. I think a couple of